Hi, this is Dr. O'Connor. Welcome to Pathways to Chemistry. So we're going to talk about covalent compounds, also called molecules. Covalent compounds have covalent bonds, and covalent bonds are the result of electron sharing. Remember when we talked about ionic compounds, we talked about the electrons being transferred from the metal to the nonmetal. In the case of covalent bonds, electrons are shared between two atoms. Many compounds are not ionic, they are molecular. Some atoms will complete their octets by sharing electrons. A covalent bond is a bond formed by sharing electrons between atoms. A molecule is a group of atoms held together by covalent bonds. Now, we talked about the octet rule when main group elements undergo reactions, and that means that they are left with a completed outer subshell of 8 electrons. So what they want to do is achieve a stable noble gas configuration. So for an ionic compound, the octet is achieved by the loss or gain of electrons to form an ionic compound. In molecules, the octet is achieved by sharing electrons. So for example, we have 2 hydrogen atoms and 1 oxygen atom that combines to give 1 water molecule, good old H2O. So we know that the valence electrons are the ones that take part in bonding. So hydrogen has 1 valence electron, and oxygen, if you recall, has 2, 4, 6 valence electrons. So we can see that each hydrogen will share its electron with the oxygen. This gives the oxygen a complete octet of electrons, 8 electrons. So what's going on when a covalent bond forms? Well, think about it. There are attractive forces and repulsive forces. So, you think of 2 hydrogen atoms, and we have the 2 nuclei, and those 2 positively charged nuclei are going to repel one another. And we also have 2 hydrogen atoms here, and each one has an electron, and those electrons also repel one another. Now, think about the attractive forces. You have 1 nucleus being attracted to the electron of the other hydrogen atom, and this nucleus being attracted to the electron of this hydrogen atom. So, do covalent bonds always form? No, they don't. Basically, your attractive forces have to be greater than the repulsive forces in order for a covalent bond to form. So the magnitudes of attractive and repulsive forces are going to depend on how close the atoms are to each other. Now, let's take a look at shared electrons and what we call molecular orbitals. We've already looked at atomic orbitals in the previous module. Molecular orbitals are combinations of atomic orbitals that are formed by adding 2 or more atomic orbitals together. Now, remember, we talked about the s orbitals, which are spherical in shape. We also talked about the p orbitals. You think about 2 hydrogen atoms. What happens if they're close enough together, the 2 s orbitals will overlap, and we end up with a covalent bond. Notice that the molecular orbital is a larger region of space than the atomic orbital. Now, we can represent this hydrogen molecule like this. We have a hydrogen, we have this horizontal line to the other hydrogen, and this horizontal line here represents the sharing of 2 electrons. We also represent it like this, and another way is to show the electrons between the 2 hydrogen atoms. Let's take a look at a bromine molecule. So we have two bromine atoms, and let's take a look at the electron configuration. Again, it's the valence electrons that take part in bonding. So what we have is we have 7 electrons in the outer shell. So 7 valence electrons for a bromine atom. Notice here, notice that 3 pairs of electrons here, and we have 1 electron on its own. So these two bromine atoms can form a covalent bond. There should be 2 electrons down here and 2 electrons down here. I think this figure here is covering that up. We have the 2 bromine atoms. So we have 2 p orbitals that overlap to form this covalent bond. Okay, here we have 2 chlorine atoms, and again we have these p orbitals overlap to form this covalent bond between the 2 chlorine atoms. Now we have a chlorine molecule, and that's what I just explained. This is what I just explained on the other slide. When we have molecules like chlorine and bromine and hydrogen, we call them diatomic molecules. They have 2 atoms. So you should memorize these diatomic molecules. We have hydrogen, nitrogen, fluorine, chlorine, bromine, and iodine. So I will expect you to know the 7 diatomic molecules. So now we'll talk about covalent bonds and the periodic table. Covalent bonds can form between like atoms and also different atoms, usually between nonmetal atoms. This is why we have so many different molecular compounds. In fact, most of the compounds that we deal with are molecular. Only a few are ionic. Here we have water. We have an oxygen bonded to 2 hydrogen atoms. We have an ammonia molecule, a nitrogen bonded to 3 hydrogen atoms. And here we have methane. That's natural gas. That's a carbon bonded to 4 hydrogen atoms. So we can define a molecular compound, all these are molecules, as a compound that consists of molecules rather than ions. In most covalent molecules, each atom will share enough electrons to achieve what we call a noble gas configuration. But there are many exceptions to the octet rule. So for hydrogen, it will always form just 1 bond. Hydrogen cannot form more than 1 bond. That's in group 1A. Group 3A, we have boron. It has 3 valence electrons. It can form 3 bonds. It can't form an octet. Group 4A, carbon, silicon, will form 4 bonds. Group 5A, nitrogen and phosphorus will form 3 bonds. But notice as we get to the 3rd period, some of these elements can form more bonds than they have valence electrons. Okay, so again, remember, we can determine the number of valence electrons by looking at the group number. But as we get further down beyond that 2nd period on the periodic table, like here at chlorine, it'll form 1 bond, but it can also form up to 3 and 5 bonds. Okay, and that's because the 2nd period, remember, that corresponds to the 2nd shell, and that can hold a maximum of 8 electrons. When you get to the 3rd period and higher, then you have those d orbitals. Here we have boron trifluoride, and it can't form an octet. Phosphorus, it can form 5 bonds, and that's more than an octet. Phosphorus pentachloride. There are 10 valence electrons. And then there's sulfur hexafluoride. There are also multiple covalent bonds. So we've only talked about atoms that share 1 electron pair to achieve the octet. There are single bonds, double bonds, and triple bonds. A single bond, as we know, is a covalent bond formed by sharing one electron pair, or two electrons. A double bond is formed by sharing two electron pairs, or four electrons. A triple bond is a covalent bond formed by sharing three electron pairs, for a total of 6 electrons. Let's take a look here. Here we have carbon dioxide. And notice here that the carbon only has 6 electrons and each oxygen only has 7. This is not stable. The same here for diatomic nitrogen. Each nitrogen only has 6 electrons. So this is where the multiple bonds come in, which we will see in a minute. So back to the carbon dioxide, we have, again, a carbon and 2 oxygens. In order for each of these atoms to have an octet, what we do is form double bonds. So here we have 4 electrons being shared between the carbon and oxygen, and again, 4 electrons being shared between this oxygen and carbon. So we can represent those 4 electrons as 2 single bonds or a double bond. So now when we count, we see that each oxygen has 2, 4, 6, 8 electrons about it, and the carbon has 2, 4, 6, 8 electrons. Nitrogen, the same thing. Nitrogen shares 6 electrons in its covalent bond. This is a triple bond. Ethylene is a compound that's used to induce ripening in fruit. And again, we see each carbon has 2, 4, 6, 8 electrons about it. And hydrogen, of course, can only have the 2 electrons. It would never achieve an octet. So another way to represent ethylene would be this way with the double bond. Acetylene is a gas used in welding, and notice the triple bond between the 2 carbons. Again, each carbon would be surrounded by 8 electrons. We also have what we call a coordinate covalent bond. This is a covalent bond that forms when both electrons are donated by the same atom. Overlap of a filled orbital on one atom with a vacant orbital on the other atom. So here we see an atom with 2 electrons. Here we have an atom with a vacant orbital. These orbitals overlap to form the covalent bond. This is a coordinate covalent bond because both electrons were donated by the same atom. The same for the ammonium ion. Ammonia picks up a hydrogen atom. The hydrogen ion is just a proton. There are no electrons. And here we have a lone pair of electrons on the nitrogen. A covalent bond forms between the hydrogen and nitrogen. This is a coordinate covalent bond. It turns out the coordinate covalent bonds are no different from any other covalent bond. So now we're going to talk about molecular formulas and Lewis structures. A molecular formula shows the numbers and kinds of atoms in one molecule of a compound: methane, ammonia, and water. A structural formula, on the other hand, is a molecular representation that shows the connections among the atoms by using lines to represent the covalent bonds. And then we have condensed structures. And these are molecular representations in which the bonds are understood by the order in which they are written. So for example, for ethane, we know that the 2 carbon atoms are bonded together. This carbon atom is bonded to 3 hydrogens, and this carbon atom is bonded to 3 hydrogens. A Lewis structure is a molecular representation that shows not only the connections among the atoms, but it also shows the placement of the valence electrons that are not involved in bonding. We call these lone pairs of electrons. These are electrons that are not used for bonding. So if we write a Lewis structure for water, we see that there are 2 lone pairs. For ammonia, there's 1 lone pair. And for carbon, 0 lone pairs. Also, a couple of things that you need to remember here, that when we're discussing molecules, a molecular formula gives the number of atoms that are combined in one molecule of the compound, whereas an ionic formula gives a ratio of ions, and that's called the formula unit. So we're going to learn how to draw Lewis structures. In order to draw them, we need to know the connections between the atoms. So for water, we need to know that the hydrogens are bonded to the oxygens. So in other words, we don't have 2 hydrogens bonded together. Usually, hydrogen, oxygen, or halogen atoms like chlorine, bromine, and iodine atoms will surround the central atom. So let's take a look at some of these Lewis structures. We have to look at the number of bonds and the number of non-bonded electron pairs. Hydrogen forms 1 bond only. Carbon, it can form 4 bonds with 0 lone pairs. Nitrogen forms 3 bonds with 1 lone pair. Oxygen can form 2 bonds and 2 lone pairs. And a halogen, fluorine, chlorine, bromine, or iodine, can form 1 bond with 3 lone pairs. So when drawing Lewis structures, first we find the total number of valence electrons of the atoms in the molecule or in a polyatomic ion. We draw a line between each pair of connected atoms to represent the 2 electrons in a covalent bond. We then add lone pairs so that each peripheral atom, except for hydrogen, because it can only have 2 electrons about it, so we add lone pairs so that each peripheral atom connected to the central atom gets an octet. Hydrogen can't have an octet. We then place any remaining electrons in lone pairs on the central atom. If the central atoms do not have an octet after all the electrons have been assigned, we need to take a lone pair from a neighboring atom and form either a double or triple bond. Now, we have to remember that molecules are 3-dimensional. We've been drawing them in 2-dimensional space. So each molecule has a characteristic shape. So what we do is use the valence shell electron pair repulsion model in order to predict the molecular shape. And how we do this is we look at the number of electron charge clouds that surround the atoms. And we also assume that these electron charge clouds orient themselves as far away from one another as possible. That makes sense because remember, you have these electron charge clouds and they repel one another. So because they stay as far away from one another as they can, this results in molecules assuming specific shapes. So for example, let's say we have these 3 balloons. Let's assume there's a central atom that forms 3 bonds. In order for those, and we call the bonds charge clouds or electron charge clouds. In order for them to be as far apart from one another as possible, they're going to take on the shape of a triangle. So each of these bond angles, if you will be 120 degrees. So we'll talk more about this in a moment. So there are 3 steps to apply the VSEPR model. Number 1, you have to draw a Lewis structure of the molecule and then identify the central atom, or the atom whose geometry is of interest. Step 2, you have to count the number of electron charge clouds that surround the atom. That includes the lone pairs and the bonding. So an electron charge cloud can be a bond, or it can be a lone pair of electrons. And then we predict the molecular shape by assuming that the charge clouds orient in space so that they are as far away from one another as possible. Here is a table that will help us with this. Here we have a central atom, A, bonded to two atoms. In order for these two charge clouds to be as far away from one another as possible, they take on a linear arrangement. The bond angle is 180 degrees. Okay? So what we have is, when they talk about the total number of groups, we're talking about bonds and lone pairs. Here we have 0 lone pairs. That means we have 2 groups and 2 bonds. That's the number of atoms. So some examples are carbon dioxide and acetylene. Here we have a central atom, and we have 3 groups, or 3 electron charge clouds. There are 3 bonds, so 3 atoms, no lone pairs on that central atom, and the bond angles are approximately 120 degrees. This is a trigonal planar arrangement. We then have a central atom here, and we have 1, 2, 3, 4 bonds. And so we have 4 groups, or 4 electron charge clouds. 4 bonds, or 4 atoms, 0 lone pairs. This is called a tetrahedral shape. Now, notice here we have 1, 2, 3, 4 electron charge clouds about a central atom, but we have 1 lone pair. So the electron pair geometry would be tetrahedral, but because we have the 1 lone pair and 3 bonds, this is called trigonal pyramidal. The bond angles are a little less than 109.5 degrees. Here for the tetrahedral, the bond angles are 109.5 degrees. And then finally, we have this other situation where we have a central atom, 4 electron charge clouds. That would make it a tetrahedral electron pair geometry. But here we have 2 lone pairs and just 2 bonds. So again, this bond angle is going to be less than 109.5. This has a bent shape. So linear molecules have bond angles of 180 degrees. So this molecule here, this is linear, central atom, 2 bonds, 180 degrees. Same with carbon dioxide. A planar triangular molecule has bond angles of 120 degrees, about 120 degrees. And that's because their clouds, the electron charge clouds, are the furthest apart when they lie in a plane and point to the corners of an equilateral triangle. A tetrahedral molecule, central atom, 4 bonds. So each one of these bonds points to the corner of a tetrahedron. And the bond angles are 109.5 degrees. So this could be methane, which is a tetrahedral molecule. Now, again, here's methane, and it's tetrahedral. It has bond angles of 109.5 degrees. Now let's take a look at the ammonia molecule. It has 4 clouds, 4 charge clouds, but one of those clouds is an electron pair. a lone pair of electrons. So let's think about this. Look at these bond angles, less than 109.5 degrees. They're 107 degrees. And the reason why is because, remember, in the bonds here, these electrons in the nitrogen-hydrogen bonds are under the influence of two nuclei, the hydrogen and the nitrogen. The lone pair is only under the influence of the one nucleus, the nitrogen. So you can think of this compressing these bonds. And then look at water. For charged clouds, it has an electron pair geometry of tetrahedron, so it's tetrahedral, but its molecular shape is not tetrahedral because we only take into account the bonds. But here we have the two lone pairs of electrons. This bond angle is compressed even further down to 104.5 degrees. So these lone pair charged clouds repel the other electron clouds very strongly, compressing the rest of the molecule, which is why the molecular shape is different than the electron pair geometry. So now we can talk about polar covalent bonds and electronegativity. So we look at chlorine and hydrogen molecules, and we know that there's a covalent bond between the two chlorine atoms, and same here between the two hydrogen atoms. And it turns out that the electrons are equally shared between the two hydrogen atoms, equally shared between the chlorine atoms. But when we look at a molecule like hydrogen chloride, it turns out that the electrons are not equally shared. In fact, they're drawn more to the chlorine. They spend more time about that chlorine. So this is where polar covalent bonds come in. A polar covalent bond is a bond in which the electrons are attracted more strongly by one atom than by the other. When charges separate in a neutral molecule, the molecule has what we call a dipole moment and is said to be polar. So because these electrons are being drawn towards that chlorine is pulling those electrons towards itself, that's creating a partial positive charge on the hydrogen and a partial negative charge on the chlorine. So electronegativity is the ability of an atom to attract electrons in a covalent bond. Here, we see that the chlorine is more electronegative than the hydrogen. It draws those electrons to itself. Electronegativity, in general, will decrease going down a group. It will increase as you go across a period. So, for example, here we have boron, carbon, nitrogen, oxygen, fluorine. Notice the increase going across the period in the electronegativity. Fluorine is the most electronegative element on the periodic table. All of the other electronegativities are measured relative to fluorine. When we talk about covalent bonds and even ionic bonds, what we look at are electronegativity differences. So if we have an electronegativity difference of less than 0.5, we say the bond is nonpolar covalent. From 0.5 up to 1.9, we say it's increasingly polar covalent. And if the electronegativity difference is 2 or more, then we have an ionic bond. Most bonds fall somewhere in between. So here we look at the carbon-nitrogen bond. And we look at the electronegativity difference, and we get these electronegativity values from that table that I just showed you. And we take the absolute value of the difference. And here we have a 0.5. And then we have a carbon-oxygen bond, and the electronegativity difference there between the carbon and oxygen is 1. The carbon-oxygen bond is much more polar than the carbon-nitrogen. Remember, this is only 0.5. Notice we put these partial positive and partial negative charges on each atom. The more electronegative atom gets the partial negative. The less electronegative atom gets the partial positive. So here's a problem. Predict the type of bond between the following: nitrogen and hydrogen. It's asking if polar covalent, which atom would carry the partial positive and partial negative charges. So we have nitrogen has an electronegativity value of 3.0. Hydrogen is 2.1. The difference is 0.9. So 0.9 is between 0.5 and 2. So the bond between nitrogen and hydrogen would be polar covalent. The partial negative charge would go on the nitrogen because it has a greater electronegativity value, and the partial positive on the hydrogen. Here's another problem. Predict the type of bond between carbon and sulfur. It turns out that the electronegativity value for carbon is 2.5, and for sulfur it is also 2.5. The difference is 0. The carbon-sulfur bond is nonpolar. Cadmium and fluorine. Fluorine has an electronegativity value of 4, cadmium 1.7. The difference is 2.3. That's definitely an ionic bond. Now we want to look at polarity in molecules. So polarity is going to be dependent on geometry, presence of polar covalent bonds, and presence of lone pairs. Polarity is important because it affects melting points, boiling points, solubility, and other properties. So let's take a look at water here. So we have very electronegative oxygen. Okay, we know the hydrogen-oxygen bonds are polar. As far as the molecule goes, the oxygen will draw the electrons to itself. It also has the 2 lone pairs of electrons. So this part of the molecule has a partial negative charge, partial positive by the hydrogens. Water is a polar molecule. Here we have chloromethane. Carbon-hydrogen bonds are nonpolar, but we have this chlorine atom here that's drawing the electrons to itself, and this results in a polarity. So chloromethane is polar. Notice it's a tetrahedral molecule. If all of these atoms bonded to the carbon were identical, then we would have a nonpolar molecule, even if the bonds were polar. That's because of the symmetry. Now, let's look at carbon dioxide. Carbon-oxygen bonds are very polar, but the carbon dioxide molecule is not polar. And that's because you have a linear molecule. Both these atoms, the oxygen atoms, are identical. They're both pulling the electrons, but in opposite directions. So the effect cancels. And sorry about that. So the effect cancels. And even though the bonds are polar, the molecule itself is nonpolar. Here's what I was talking about before. You have this tetrahedral molecule. We have polar bonds, but they cancel out. The molecule is nonpolar. Here's another linear molecule. In this case, we have the very electronegative nitrogen pulling the electrons towards itself. This molecule here is polar. Again, when you have a linear molecule, and if the atoms bonded to the central atom are different, you're going to have a polar molecule. Let's take a look at formaldehyde. So we draw the Lewis structure for it, and we know it's planar triangular or trigonal planar. And in this case here, these atoms bonded to the central atom are not identical. And the electrons are displaced to the more electronegative oxygen. So this results in a polarity. This molecule is polar. It turns out that likes dissolve likes. So what that means is polar substances will dissolve in other polar substances. So water and alcohol are both polar. So alcohol will dissolve in water. But nonpolar will dissolve nonpolar. So oil will not dissolve in alcohol, but it will dissolve in a solvent like hexane. So again, polar will dissolve polar, nonpolar will dissolve nonpolar. So here's a question. Will methane dissolve in water? We have methane, it's tetrahedral, and the atoms bonded to the central atom are the same. This is a nonpolar molecule. Water, we know, is polar. So, no, methane will not dissolve in water. Nonpolar and polar do not mix. Now we're going to name binary molecular compounds. Binary molecular compounds are compounds that are composed of two different atoms, two nonmetal atoms. So what you need to do is memorize these prefixes. So if you have one atom, that's mono, 2 is di, 3 tri, 4 tetra, 5 penta, 6 hexa, 7 hepta, 8 octa, 9 nona, and 10 deca. What you do is the less electronegative element is written first. The first element in the formula, you would name it and then use a prefix to indicate the number of atoms. If there's only one atom for that first element, don't use mono. Name the second element in the formula, use the ending "ide", and use a prefix if needed. So for example, here we have 2 nitrogens and 2 oxygens. 2 is di, 5 is penta. We have dinitrogen pentoxide. Because of the 2 vowels, oxide begins with an O, we drop the A in penta. So dinitrogen pentoxide. Here we have a boron with 3 bromine atoms. So this is called boron tribromide. Again, for the first element, we don't use mono. Here we have sulfur trioxide. Here we have sulfur hexafluoride. So you should be able to name these molecular binary compounds.